Okay, you guys, we've got our vector field with f. It has components e to the y, e to the negative y, and e to the z. C is the boundary of the plane x plus 3y plus 3z equals 3 in the first octant, and we are asked to use a surface integral, right-hand side of Stokes' theorem. The usual, I mean, you could switch it, so it doesn't necessarily have to be the right-hand side, right? But it's the side with the curl in it, to evaluate the line integral. And we assume C is oriented counterclockwise, so Stokes' theorem works. So let's write down Stokes' theorem. So you're taking a test. Let's say you freeze up. You have no idea what to do. But you've memorized what Chamberlain asked you to memorize. So write down the appropriate theorem that you think you need to use here. So Stokes' theorem says what about the line integral with respect to the vector field? So symbolically, that's the line integral. With respect to f, so it's what kind of integral? It's a surface integral, right? Curl of f dot n ds. So write this down. It gives you a place to start. So in fact, what does the right-hand side of that statement tell us we need to find? Curl of f, right? And then if we use the calculation formula, del g as well, right? Let's go ahead and draw the surface. That's a good skill to know how to do and to review as well. So let me do this. So we're just in the first octant, so I'm just going to draw the first octant here. So x, y, z. Okay, so I want to draw the plane, and C is the boundary of that plane in the first octant. So what would be a good way to draw the plane, the part of the plane that lies in the first octant? Just x-intercepts, connect them, yeah. So what's going to be the x-intercept? 3 if you plug in 0 for y and z, so I'll go up. 3, there's your x-intercept. Y-intercept and the z-intercept, the non-zero coordinates are both 1. So we'll go 1, 1. And then it's oriented that way. Okay? So that's C. C is actually 3 different pieces, right? It's comprised of 3 different line segments. Thankfully, though, we're not evaluating this guy directly. It would require us to evaluate 3 different line integrals over each segment that I've drawn here and add them together. So it could be done, but it'd be a hassle. So the idea then is we can take the surface that C surrounds. In purple here, that's just part of the plane. We could consider that our surface, which should be easy enough to work with, and use the right-hand side of Stokes theorem. Now, you do have to be careful here. Let's just find curl, and then I'll tell you where you have to be careful. So the curl of f, what is that? Del cross or dot f? Cross. Okay, so I, j, k. What do I put in the middle? ddx, dy, ddz, the differential, right? Or not even differentials, the differential operators, I should say. And then the components of f on the last row, e to the y, e to the negative y, e to the z. Okay? Well, if we cross out first column and take d dy of e to the z and subtract off d dz of e to the negative y to get the first component of the curl, what do we get? We do get 0. So 0i, or if you like, you could write it in component form. And then if we cross out the middle column and take the pseudo-determinant that corresponds with what we have there, what do we get? ddx of e, so this guy, ddx of e to the z is just 0 minus ddz of e to the y. 0. So there would be a minus in front of it, right? You do have to not forget that, but in this case, negative 0 is the same as positive 0. Pretty sure. I don't know much, but I know that. Okay, and then maybe we'll get something non-zero for the last one. So if we compute this, d dx of e to the negative y is 0, right? Minus d dy of e to the y? E to the y. So it's just negative e to the y for the third component. It would be easy to mess up a negative there, but just double check it. All right, so the calculation formula, remember, we're going to project this into the xy plane, that surface, and we'll call the region that we end up integrating over R generically. And then it is a flux integral where the vector field is the curl, so we can replace n with either del g or negative del g. Which one is it? Del g, because it's oriented upward by assumption. So your normal, a sample normal vector, they'll all be the same. It would look like that, right? So k component has to be positive, so del g as opposed to negative del g, right? So, okay, let me remind you, the surface, let me see if I can squeeze it in here. The surface that we integrate over in a surface integral, we think of that as given by z equals lowercase g of xy, right? And then we get what we call uppercase g of xyz by, if we want the upward orientation, we subtract g of xy. And technically that's what we call we subtract lowercase g of xy, and that's what we call uppercase g of xyz. And the idea is we set that equal to 0. And we think of that as a level surface of the 3-input variable function, uppercase g of xyz, right? And we know that if we take the gradient of that, the vector we get will be normal to our surface. Okay, so in order to have this or this, I need a 1 in front of my z, don't I? So that's what we can't forget here. We need to divide. So let me shrink some of this stuff down.
Why do you need a 1 in front of your z?
We currently have a 3, and we need to use the correct formula. Okay? So this is the thing we take the gradient of, not 3 times z, right? It won't be quite right if we do that. So divide this thing by, I don't think we don't actually want to get g of xy on the other side. We want to have everything on this side, but just divide everything by 3, and I think you'll get there. So yeah, we'll get g of xyz equal to what? 1/3 x plus y plus z. Technically, I suppose you'd subtract off the 3 and set it equal to 0 first, or second. Everybody see that?
Wouldn't that be 1?
It should be 1. What did I put? Oh, yep. No, it doesn't matter, but it will matter in other cases, so let's be correct here.
And it would work if you did the opposite of all that, right?
You would have a problem with your orientation if you did that, as long as you fixed it, yeah. So I know that the k component, when I take del g, the k component is going to be positive, right, which is what we need to have the right orientation. So what's del g going to be? 1/3, 1, and 1. Okay, so then our formula tells us to do what? Take the dot product. So I'm going to dot product. This is my curl. This is my del g. So let's take that dot product. Curl of f dotted with del G. What's that going to equal?
0, 0, negative e.
Um,
Or negative e to the y. Because 0 plus 0.
just negative e to the y. There you go. Everybody buy that? It's not such a bad integrand, is it? Now, when we project this thing down, I'm going to set up the integral in just a second. When we project this surface down, what do we get in the xy plane? Yeah. What does that triangle look like? There you go. 1, 2, 3, and then up 1. So that this is our region outlined in orange here. This is our region, right? And let me go ahead and put in a representative, just a vertical rectangle should do here. What function is going to give you the top of that rectangle? Yeah, so if you look over here, just put in 0 for z, right? When you project it down in the xy plane, that's what you're doing. And then solve it for y. If you solve that for y, well, first you'll have x plus 3y, z is 0 equals 3. 3y equals 3 minus x, so y, I'm going to write it as 1 minus 1/3 x. Or you could take 3 minus x, divide the whole thing by 3, it really doesn't matter. So that's going to give you the top of the rectangle. Of course, height-wise, 0 gives you the bottom. So let's set up our integral then. So according to Stokes' theorem, this line integral is equal to the double integral over r. What are we going to integrate from? 0 to 3 on the outside. And then y goes from 0 to 1 minus 1/3 x on the inside. Our integrand is just negative e to the y. Can I pull that negative out? Was it negative y?
Yeah, no, it's negative e to the y.
Okay. So a different component was negative y. Okay, that's what I'm thinking. And then dy dx. Okay. Any questions about that? Let's go ahead and evaluate it just because it doesn't hurt to see me do one since you have a final coming up in 2 days, right? So this is a review of a chapter 15 problem when you're evaluating this integral. Okay, integrate with respect to y, what do you get? We'll still leave the negative outside, the first integral symbolism outside. Yeah, you integrate e to the y with respect to y, you get e to the y, but it's evaluated from 0 to 1 minus 1/3 x, like that. Okay, careful, when you plug that in, what happens?
Still have a function on top. It's like a weird 1/3.
So e to the 1 minus 1/3 x, and then minus 1, because e to the 0 is 1, right? dx. Everybody buy that? Okay. As long as it's not too expensive, right? Okay. You'll still buy it. I've got some land in Arizona you can buy. Yeah, it's oceanfront property. Okay. If we integrate, okay, be careful here. When you integrate e to the 1 minus 1/3 x with respect to x, what are you going to end up with out front? Negative 3? Yeah. Now, can you check that really easily? Just take the derivative. Oh, it's e to the 1 minus 1/3 x times the derivative of that exponent by the regular chain rule, right? And then that negative 3 should cancel if you do that, and it does. So that you get back the term you had in the previous step, right? So you can check that. And then minus x. Yeah, I think that's a good idea because then they'll just obliterate each other, those negatives, right? Well, yeah, I got to make it exciting, use descriptive words. They'll obliterate each other. So 3 to the 1 minus 1/3 x plus x inside the evaluation brackets. Okay, so plug in 3, and what do you get? Numbers. You better get a number for a definite integral, right? You better. Okay, so we get 3 plus 3, okay, minus 3, just e to the 1, and then 0 there. So we get, when all is said and done, 6 minus 3e. So here it all is in one shot, I think.